Okay, we have here another integral on the board. I've got the integral from 0 to infinity of sinh 3x times e to the minus 4x dx. Okay, you may know where I'm going with this. I had a problem very similar to this just a few days ago. And what I want to notice with this is the similarity to the Laplace transform. Okay, now we have here a definition for the Laplace transform on the board. And you'll notice the similarity between the integral. We have the same bounds. We have something like this exponential term. And by doing this, it's going to simplify our work quite a bit because we can use the Laplace transform table with some common formulas. And we should be able to do this pretty quick. We'll be able to get this into a function in terms of s and then solve it. So now just looking at our original integral here and looking and comparing to our Laplace transform, f of t is going to be this sinh of 3x. So we have that value here. And then we have e to the minus 4x as opposed to e to the minus st. You know, our variable here is x and here it's t, but that's not going to bother us. So what we can do, just comparing here, we can notice that our s value is going to be just 4. And so with that f of t, what we're doing is we're looking for the Laplace transform of just sinh of 3x. But there's a nice formula for this that's going to help us out, and it's just going to be that the Laplace transform of sinh of, we'll say, at is going to be the same thing as a over s squared minus a squared. So for the Laplace transform we want to find here, our a value is just going to be 3. So we have a is 3. So then using this, we can say that this Laplace transform, which is our integral, is going to be the same thing as 3 over s squared minus 9. But of course we have a definite integral here, so we're going to want to get a number. And the Laplace transform, it gives us a function in terms of s. But that's not really a problem, as we have an s value. So all we need to do for our function here is we just need to calculate f at s equals 4. So we just want f of 4. So we can just plug a 4 in here. And so to calculate this, we're just going to have 3 over 4 squared minus 9, which is going to be the same thing as 3 over 16 minus 9, or 3 over 7. Okay, so like I said, that went really quick, but that's really only because we had this formula, right? This saved all the work for us, and you might be saying that's kind of cheating to just use a formula for an integral. But anyway, for the people that think this is too much of a shortcut, I think what I'll do is just derive this formula right now. So what I want to show here is the Laplace transform of sinh of at, where a is some constant value on our variable t. I want to say that it's equal to this. And by the definition of the Laplace transform, we can put it into the forms of the integral. So what I'm going to do is just solve this integral in order to get this formula. And what I'm going to do for this is integration by parts, and we'll use the DI method or tabular integration. And we could do this either way, but what I'm going to do is I'm going to choose to integrate e to the minus st, and we'll differentiate sinh of at. So first let's take the derivative here, and this is going to give me cosh of at, but with the chain rule we need to bring an a out front. And then we'll do it again, differentiating again, we're going to get sinh of at. Again, chain rule, this is going to become a squared. Integral of e to the minus st, we're going to have e to the minus st, but then we're going to have a minus s in the denominator. I'll write the minus sign out front, and then we'll just integrate one more time. The minus is going to become a plus now, and this is going to be e minus st over s squared. We're going to have part of our solution here on the diagonals. What I'm going to do is I'm going to factor out an e to the minus st, and I think I'm also going to factor out a minus sign as we have it in both these. So we'll write minus e to the minus st in front. Then let me do this carefully. So I'm going to have sinh at over s, and then here we're going to have a plus sign. This is going to be, let's see, this is going to be a over s squared cosh at. And we're just going to evaluate this from 0 to infinity. And then here, this line here, this is actually going to be an integral. And because a squared and s squared are constants, I can bring that out front of the integral. So I have it like this, a squared, s squared, integrating from 0 to infinity. And then we're going to have just sinh, that's a weird I, but okay, sinh at e to the minus st dt. But now you'll notice here, this integral actually, this is the same thing as what we wanted to find. This is the same thing as our Laplace transform. And I'm just going to abbreviate this with my cursive L here for Laplace transform of this thing, the thing that we want to find. So I'm just going to rewrite this, and we can't forget we have this a squared, s squared on here. Okay, so now what I'm going to do is I'm going to just try to evaluate this piece. And first we're going to start by trying to evaluate it at infinity. Now typically with Laplace transforms, we're fortunate with the infinity because we have e to the minus st here. We plug infinity in here. E to the minus st, this is going to 0, assuming s is greater than 0. So we usually make that assumption that s is greater than 0, and then this is okay. But we've got a little bit of weird business here because we've got sinh and cosh, and we need to think about this a little more. So let me just kind of write this down. Sinh of AT is going to be e to the AT. I'm not going to worry about the s. We're just going to think about the sinh. This is going to be e to the AT minus e to the minus AT. And we're multiplying in e to the minus st. I'm going to drop the minus sign in the s's for the second just to get a sense of what's happening here. So when we distribute in this e to the minus st, we're going to have e to the a minus st. And then here we're going to have minus, and this is going to become, I'll bring the minus out, and I can write this as s plus a t. And now you can see the potential problem. If we're evaluating an infinity, if this is positive, it diverges, we get an infinity here. And then if this becomes positive, this is also an infinity. So we have all kinds of troubles with infinity unless we put some conditions on this. So here, we're fine as long as s is greater than a, right? Because if s is greater than a, then this piece here is negative. We have a minus sign on the t, so this would be going to 0. And then here it's just a little more complicated. We're going to need s to be greater than absolute value a. The reason we can't just use s greater than a here is like kind of let's just make a pretend scenario here. Let's say s is 5 and a is minus 6. Now at this point, of course, s is greater than a, right? So this criteria is fine, but it doesn't meet this criteria because if we take the absolute value of minus 6, then 6 is actually greater than 5, and this doesn't work. The reason we need to do that, if you plug in 5 and minus 6 here, you get a minus 1 here. Okay, minus times minus is plus. Now you get a positive t. Now you're just looking at e to the infinity, and that goes off to infinity. So it turns out we need this condition right here, or else this whole integral is going to diverge. And you just notice going back to the original integral, right? We had a here is 3, so s is greater than absolute value of a. 4 is greater than 3, so we're fine. This right here is actually really easy to see if you look at a graph. If you look at a graph of this integral, it's clearly like going off to 0. It's got a shape kind of like, the graph of this is very like going to 0. If instead we change this 4 to a 2 and you had e to the minus 2x here, it's a totally different graph. It's like this. And because we're going from 0 to infinity, the area here is clearly infinite. So I just need to capture this condition right here and then we can continue. Okay, so now that we set up this condition, then everything at infinity, these are going to 0. The sinh term and the cosh term, they're both going to 0. Those are all going to 0. Now we just need to evaluate at 0. So we're going to have a minus times a minus here. That's going to give me a plus. E to the 0, this is just going to be a 1 in front. And then we're going to be looking at sinh. We'll plug in a 0, so we're going to have sinh of 0 over s plus a times s squared. And this is going to become cosh at 0. So let's just look at sinh at 0 real quick using the definition. So this is going to be the same thing as e to the 0 minus e to the 0 over 2. Well, this becomes 1 minus 1 over 2 or just 0. So this piece is going to 0. And then we'll do the same kind of thing for cosh at 0. So plugging in e to the 0, but now the minus sign, this is actually a plus here. So this is going to be e to the 0 plus e to the 0 over 2. Well, this becomes 1. This becomes 1. We end up with 2 over 2. Or just 1. So this here is just a 1. So just cleaning this up, this whole thing again is equal to this Laplace transform. I'm just going to shorthand it with a big L. And this here is actually going to become just 0 plus a over s squared. So I'm just going to have a over s squared plus a squared over s squared of our big L. Well, I can subtract this thing on both sides. And so on my left side, I'm going to end up with 1 minus a squared over s squared of this L thing. And then we're just going to have this on the other side, a over s squared. I can get a common denominator here by writing my 1 as s squared over s squared. And what I think I'll do, I'll just kind of bring this together because I'm running out of space a little bit. So we'll just combine these two fractions, right? And so in order to just isolate this, our goal to get our solution, what I'll do is we'll multiply here by the reciprocal of just s squared over s squared minus a squared. So this stuff cancels out, but we have to do it on both sides, okay? But now what's gonna happen is our s squareds are gonna cancel, and we're left with just our solution of a over s squared minus a squared. And of course, we just have to remember this condition. And this is the same as this, and that's our formula for the Laplace transform of sinh of AT. So that's it, we'll stop it there. Thanks everyone for watching today. Please like and subscribe. Have a great day.